I'm Tim Sweeney, and for my journal paper presentation, I selected Mamba Linear Time Sequence Modeling with Selective State Spaces, written by Albert Gu and Tri Dao from Carnegie Mellon University. So just like a little bit of background, right now the current state of the industry is that the transformer is the dominant model. The transformer basically came from a paper that was published called Attention is All You Need. It was published in 2017. It came out of Google. And basically, it allowed for AI as a commercial product like that we are now familiar with from all these different companies that are pushing large language models. Um, Now, Mamba is an attempt to supplant the transformer with a more efficient, faster model with similar performance. And so, where the transformer, or I'm sorry, where the Mamba model comes from, is from a state space model. This paper is not the first paper to introduce the state space model, but basically, it's a neural net that's based on um, classical control system theory state space representation. So that's what we have at the top of the slide here. This is a state, or this is a plant representation. Uh, yeah, just like a classical plant representation that can be described by these equations, which are the linear time invariant state space model equations. And you can see that the equations for the Mamba model, which are here at the bottom, very closely resemble these equations. Um, and so this is the model architecture as described in the paper, where A is like the state transition matrix, and it describes how the internal states of the model transition from time step to time step. B is a projection from the input, which is X, to the hidden states, and then C is a projection from the hidden states to the output. All of this structure of of the hidden states and the inputs, the B matrix, the C matrix, and the outputs, and the discretization matrix. These have all been described in previous papers, which brought forth the state space model neural net. The iteration or the innovation that this paper puts forth is this selection mechanism highlighted in blue. And the selection mechanism allows for the model to have the benefits of input data compression that you would get from a convolutional model or recurrent neural network, while also allowing for a very large context window. So the large context window is what the transformer gives us through its attention mechanism. The state space model gets that same sort of attention mechanism through this selection matrix, which is a fully connected affine layer. Um, so in terms of time complexity and memory usage, the transformer is O of n squared, whereas Mamba is O of n. So as your sequence lengths increase, your memory and time complexity increases quadratically with the transformer, while it increases linearly with Mamba. The model was evaluated on three different domains, and I will talk through two of these because the audio waveform domain is very similar to the language domain. But it was basically compared on language, DNA sequencing, and audio waveform generation and recognition. So this is a part of the language model performance test. This was an induction heads extrapolation test, which is a standard benchmark for neural nets. You can see that the Mamba model was actually able to perfectly complete the induction heads um, benchmark test. And from the paper, it says that the model was able to generalize perfectly to million length sequences, or 4,000 times longer than it saw during its training, while no other model goes beyond 2 times. And so, why this is so effective is because of that selection mechanism that the model trains on. It perfectly is able to remember data from earlier in a sequence that it sees later in a sequence and be able to predict the correct output or the correct sequence that follows a previous sequence. This is a table that shows like as you increase your model size, the ability of the model to perform a zero-shot evaluation improves. So the accuracy of the zero-shot evaluation task improves as all of these models increase. However, at comparable sizes, the Mamba model outperforms all the other models. And these are a mix of transformers and convolutional networks. So the model performance benchmark for the DNA test, the top shows that the performance improvements of Mamba over the Transformer Plus Plus and Hyena DNA models. And this top chart shows how the models perform as we increase the model size. So on the x-axis here, we have the parameter, the number of parameters in the model. And then on the y-scale, we have perplexity, which is its ability to accurately make a prediction. And you can see that Mamba has significantly less, significantly lower perplexity at the same size and equivalent perplexity at smaller model sizes. And then this bottom chart here is an investigation into model performance after training on longer sequences. And we see that the Mamba model is actually able to make use of sequences that are significantly longer than the Hyena DNA model is able to make use of. So as we train on much longer sequences, the Mamba model continues to be effective and reduce its perplexity. Here we have a speed and memory test. And we see that the Mamba model is significantly faster, both in training, which is this top diagram here, and then also inference, which is this bottom model here. And from the paper, we're told that the Mamba model achieves 4 to 5 times higher inference throughput than a transformer of similar size. And for example, a Mamba model of 6.9 billion parameters would have higher inference throughput than a 5 times smaller transformer model, which would be like 1.3 billion parameters. And so the paper was released in 2023. So far, no major LLM has fully adopted it, but there is a trend towards using hybrid transformer Mamba models, such as Jamba by AI21 Labs. And there is a lot of research continuing in this area. Thank you.